the instability issue of the CPM controller comes with the topology itself, and we can try to introduce some advanced control methods to resolve this issue. So in this section, we are going to study how can we add an artificial ramp to solve this instability issue of the CPM controller. So basically, the instability of CPM is not dependent on the specific topology. So different topologies, they all have these issues. And we can resolve this issue by introducing the ramp, right? So controller can be rendered to be stable, right? To be stable by adding an artificial ramp. So next, let's look at what is this artificial ramp, right? Artificial ramp. So we use the extracted circuit from the main topology. So we only care about the sensing of the transistor current. Let's say that we have the transistor here in the topology Q. This topology could be buck boost or either buck boost, whatever. So for the CPM control, right, we need to sense this transistor current here with the sensor gain of RF. And this output goes to a comparator. And the output of comparator goes to the latch, right, a SR latch. So reset, set. And the latch, the setting signal comes from clock. And the other output, the other input of the comparator comes from the compensated error signal between the output voltage and reference, right? So I will no longer plot the complete compensator network and the sensing network for the output voltage. For this operation, right, adding the artificial ramp means that we made some changes, right? We break the loop here. So by adding a operator here, I will use the red line, right? Operator here with adding the artificial ramp, right? Adding the artificial ramp. So here we generate a ramp also from the clock signal and add this ramp into the sensed transistor current signal and then feed this sum into the comparator. So this we call the red part, we call it as ramp compensation. And also the output of latch goes to the gate driver, right? Generate the driving signal and goes to the gate of the transistor to control the on and off of the switch. Then we look at how the ramp compensation works. So basically, we have the time domain waveform, right, t, and we look at this red parts. So the ramp is generated synchronized with the clock. So the switching cycle of the ramp is also Ts. And here is the artificial ramp, IA, right, IAT. IAT will be very simple. So for each switching cycle, it rises linearly from 0. And for the next switching cycle, it's reset to 0. And then for the following switch cycle, it rises again linearly. So the slope of this straight line is MA, right, which is the slope of the ramp. So this is like a ramp. That's why we call it ramp compensation. Okay, next, let's look at how it works. So the artificial ramp. Artificial ramp works so that we plot the inductor current and the controlling current respectively. So the red line is the controlling current, IC. And here, right, here it's like the inductor current is compensated by this ramp, right, by this ramp. So therefore, we will have compensated, right, ramp compensated controlling signal. And the slope of this ramp is minus MA. Then it's like the inductor current is compared with this a modified controlling signal, right? Controlling signal. So we can also plot the inductor current waveform. So starting from IL0 and rises linearly. Right? Rises linearly with the slope of M1. And when this condition fulfills, it's like IA DTS plus IL DTS equals to the controlling signal, ICT. This triggered the transistor turn off, so I line here. So this moment is DTS. So when this happens in this moment, right, IA DTS plus IL DTS equals to ICT, right? Then transistor turn off. So if the transistor is off, the inductor current will drop linearly, right? Drop linearly until it reaches the TS, right? TS. So the slope here will be equals to minus M2. For steady state operation, steady state operation means that the starting current equals to ending current here, right? Equals to the ending current. So no net change occurs over one switching cycle. Okay. And also based on this formula, right, we can also see that derive the expression for IL DTS, right? IL DTS will be equal to IC minus IA DTS. So I waveform is plotted here, right? Plotted here. So that's the basic principle of the ramp computation. Okay, so in this section, we have studied the operating principle of the ramp computation and how can we add this ramp on top of the previous mentioned CPM controller. And the next section, we are going to study how to analyze this ramp computation.